We are now starting the last major topic of this course, PDEs. We are first going to be going through some introduction on PDEs in this video. As ODEs were equations that told us something about a function by actually talking about its derivatives, the same thing can be said about PDEs. The main difference is now that the function we have, that I'm going to be denoting by u, is a function that goes from Rn to R. So u depends on more than one variable. It can be depending on the xy plane, or on x and time, on the xy plane and time, and so forth. It can have as many variables, it can be depending on as many variables as you want. Usually the higher the number of variables, the more difficult it is to solve. But in general, this is what a PDE is. And when you're looking at an equation that restricts u, the equation that you're looking at involves the partial derivatives of u. So for example, we can take u that goes from the xy plane to r and give some restrictions on the second derivatives of u and how the partial second derivatives of u combined work. So for example, second derivative of u with respect to x plus second derivative of u with respect to y is equal to a function that depends on x and y itself. We can write this, as we did for the ODEs, as a differential operator L applied to u equals to f, with the operator L being the sum of the second derivative with respect to x plus the second derivative with respect to y. In this case, is a linear operator. You see how you don't need to write u explicitly in there. So let's look a little bit more into terminology. The first thing we're going to be looking at is the difference between a linear PDE and a non-linear PDE. A PDE is linear if the associated differential operator is a linear operator. So we have already seen what it means to be a linear operator. When you apply it to a sum of two things, then it's the same as applying it to the first thing plus the second thing. And if you apply it to something that is a constant times u, is the same thing as saying that you're taking the constant times L applied to u, for any value of the constant for any u. The second thing is homogeneous. That is also fairly straightforward with what we have seen in ODEs. It just means that the right-hand side is equal to 0. We can also talk about forcing term. The forcing term of a homogeneous equation is equal to 0. Then the order of a PDE is the highest partial derivative used. While for ODEs, there is only one type of derivative that is in play, for PDEs, there are all the partial derivatives. The order of a PDE is really the highest of them, not only the highest with respect to a specific variable. So for example, second derivative of u with respect to x is a second order PDE. d squared x u plus d to the third with respect to x, y, and z u is equal to 0 is third order because your second term is of higher order than your first term, even if the second term is mixed. We will spend a lot of time, pretty much all the time that we have this course, talking about second order linear PDEs. So we are restricting ourselves to only looking at things that are linear and don't have any term higher than second order. That means that it has to have to be of this form, with A, B, C, D, E, and capital F being constants, and F being a function depending on x and y. I actually did not specify that we're going to be restricting ourselves to 2 dimensions. It could be higher. All the things we're going to be talking about can be extended to higher dimensions. Most examples we're going to be looking at stop at 2 dimensions just because going at higher dimensions is just very cumbersome notation. So this is the most general second-order linear PDE in 2 dimensions. It has all the first-order derivatives and all the second-order derivatives. When we look at second-order linear PDEs, we kind of forget about first-order terms and zeroth-order terms, and we concentrate on the second-order terms. This is intuitively because those are the terms that mostly define the behavior of the PDE. So we can write these second-order terms in this fairly odd way as a matrix product. We are looking at a vector of partial derivatives times a matrix of coefficients times another vector with the same partial derivatives. And we look at the center matrix and we talk about this matrix M in order to determine the behavior of our PDE. We're going to explain later why we can always assume M to be symmetric. But we're looking at this matrix and we're saying that depending on the determinant of this matrix, then we have different types, different classifications of PDEs. If the determinant is equal to 0, then we're going to talk about parabolic PDEs. If the determinant is positive, we're going to talk about hyperbolic PDEs. And if it's negative, we're going to be talking about elliptic PDEs. We're going to explain further why these 3 distinctions matter. They hold in 2D. We're going to explain later how to extend it in higher than 2D. It's interesting to see how the mathematical behavior, so the distinction between parabolic, hyperbolic, and elliptic PDE, corresponds to a difference in the physical models that they are showing. So a parabolic PDE corresponds to a diffusion equation, so something that starts at one point, it gets dragged around your domain. A hyperbolic is a wave equation, and the most obvious representation is really, it's if there is a wave at some point in time, it just keeps moving over your space. Elliptic has a much more complicated behavior, and we're going to be seeing it later. To me, it's less obvious what it represents, but it's in the physical model represented by the Laplace equation.